Good morning. Welcome to the first talk this morning, which is by Abdul Basit from the University of Notre Dame, who will talk on rank bounds for design matrices and applications.
Yeah, thank you. Right. So the applications I plan to be talking about are going to be incidences. So I'll start off with those. Here's the usual setting. We have a set of points in, say, R2. And for any R bigger than 2, we say an R-rich line is a line that contains exactly R points. And we say TR is the number of R-rich lines. And now the general question we want to ask here is, what can we say about TR? So this is a somewhat different setting of incidences than we've seen so far. So I'll take things slow. But both of them are very related to each other. So for this talk, I'll be focusing on T2. And we say a line that has exactly 2 points is an ordinary line. So we'll be talking about the number of ordinary lines. Okay. So this is probably one of the oldest theorems in geometry, combinatorial geometry, is the Sylvester-Gallai theorem, which says if I have a finite set of points, that determines no ordinary lines. So T2 is 0, and every line has 3 or more points. Then the only way this can happen is if all my points lie on a line. So the statement was originally conjectured by Sylvester, and then later on also by Erdős. So yeah, the story is a bit confusing because Melchior proved it before Erdős conjectured it. And apparently Erdős didn't know about the result. So yeah, and now we have many, many more proofs. So I'll show one proof by Kelly. So it's a really nice proof, and I think people should know it. Right, so here's Kelly's proof. Goes by contradiction, so we assume we have a set of points, and every line has 3 or more points on it. Now I find a point and a line pair such that the distance between the point and the line is the smallest non-zero distance. So let's say I have a point-line pair. Right, now I must have that L should contain at least 3 lines. So here's 3 points on my line. And now it's sort of easy to see the contradiction because I can find another line, L prime, and I know that the distance between R and L prime is smaller, so I get a contradiction. So that's a really simple proof of Kelly's of the Sylvester-Gallai theorem. Right. So sounds simple enough so far. What else do we know? Well, we can count the number of ordinary lines. So suppose I have n non-collinear points. How small can I make T2? So we know it can be 0. Can we get an actual lower bound on it? So for example, if I have n points on n minus 1 points on a line, and 1 point off the line, then I should have n minus 1 ordinary lines. And more generally, if I have n minus k points on a line and k points off the line, then it's sort of easy to get this bound k times n minus 2k. And it gives a linear bound when k is between 1 and n over 2. So things are fairly simple, but then things get complicated. So as soon as k becomes n over 2, things get a bit trickier. So for example, we have this configuration. It's called the Böröczky construction. So you start off with some number of points uniformly spaced on a circle. So in this case, we have 6 points. And now I look at, so now every line is ordinary so far, but I'm going to add a bunch of points and try to make things, try to get few ordinary lines. So here's what I do. I start looking at the diagonals. So I have 3 diagonals here, and all of them intersect at a point at infinity, so I throw in that point. And I keep doing this for every set of diagonals. So right now, all these lines have 3 points on them, but I add another point, but now, well, the green lines become 3 rich, but now I create 2 more lines, the red ones, which are ordinary. And I can keep doing that for every set of diagonals. Right, so I get this set of points, and yeah, sort of messy, but the green points have no ordinary lines through them, and the red ones have 2 ordinary lines through them. So it's sort of easy to check. I have exactly 6 ordinary lines. So, and in general, you can generalize this construction to any arbitrary n. Things become different when you have odd versus even, but it still works out. with the lower bound, it turns out is n over 2 here. And this was conjectured to be the best construction. That, yeah. So that's what the Dirac-Motzkin conjecture said, that if n is bigger than 13, then any set of endpoints in the plane will have, and non-collinear points in the plane will have at least n over 2 ordinary lines. We need n bigger than 13 because there's some small configurations that behave badly. So, for example, both of these, I have 7 points here with 3 ordinary lines and 13 here with 6. And the conjecture is that aside from these guys, every other point set should have, well, if n is big enough, every other point set should have n over 2 ordinary lines. Okay. So a lot of people worked on this for a long time. And so, for example, this was a sequence of results. We knew at least 3, at least square root n, linear. And then more recently, Green and Tao showed the following. They said for a large enough point set, you should have at least n over 2. So they didn't get down to 13. And not here is some large number, but it still works. And yeah, so they showed you must have n over 2 ordinary lines. And they showed something a bit stronger. They actually showed that if you have n over 2, then the only way you can achieve that is by using the construction that I showed before. So it's a much more stronger result than what I state here. And they had a more general result as well, which sort of gives an algebraic structure to the whole thing. And which is the reason I decided to talk about it here as well, is that if I have few ordinary lines, then most of my points should lie on a cubic curve. So somehow the only way you can minimize things is by minimize the number of ordinary lines, is by having a lot of group structure going on. Right. So that was Green and Tao. Okay. So that's pretty much the situation over the reals right now. Good. So you can also talk about the same thing over complex numbers, but it turns out the theorem itself doesn't really generalize to the complex numbers because of the following configuration. So this is called the Hesse configuration. You can look at it as the inflection points of a cubic curve, and it turns out, well, you have 9 points and exactly 12 lines, and all of them are 3-edged. And you can embed this in the complex plane by using these coordinates, or the inflection points of any cubic. So this shows that the Sylvester-Gallai theorem by itself doesn't generalize to the complex numbers. But we can say something, and that is what Kelly did. He said, well, if you step up a dimension, then things still work out. So if I move to complex space, and now my condition says, well, the points are not coplanar, then I must have an ordinary line. So in some sense, things are still holding in the following way, that if I have no ordinary lines, that's forcing my points to be in a low-dimensional space. The dimension goes up by 1, but it still says something. Right. More recently, Dvir, Saraf, Wolf, and myself, we were able to prove a lower bound on the number of ordinary lines. So we showed the following two things. If I have a set of points in d dimensions, complex space, and all the points don't lie on a plane, then you must have a linear number of ordinary lines. And then if you go up even more in dimensions, so if you have a point set that's sort of not clustered in a 3-dimensional space, then you should have pretty much all the lines should be ordinary. So that's the best you should be able to say in higher dimensions. And there still might be room here for non-coplanar points. I don't really know what the answer should be, but this is the first step. So. Okay. Right. So a lot of people spend a lot of time trying to generalize these and look at things. So here's some of the generalizations that I think are interesting. So for example, here's something called the quantitative Sylvester-Gallai. So now, so before for Sylvester-Gallai, I had the restriction saying every line should be 3-edged. Now we can say, suppose that for every point, most of the other points lie on 3-edged lines. So for more formally, if I fix a point, there's delta n other points that lie on 3-edged lines. And now what can we say about the point set? So for the Sylvester-Gallai theorem, delta was 1. What if we have somewhat weaker things? And then it turns out it's still enough to force my point set to be low dimensional. And we can show that people can show that the point set should have dimension order 1 over delta. And this is tied up to constants. I think the constant here is 12, so you might be able to improve the constant, but asymptotically it's tight. Right. There's another version which is called the stable Sylvester-Gallai. Doesn't have anything to do with model theoretic stability, but what this is saying is, well, now you can think of tubes. So instead of lines, well, for every point, for every line, I have, how do I want to say this? Yeah. For every point, I look at every other point, and there's a third point that's almost collinear with this. So most of my points lie on around thin tubes around every line. Then we need this distance condition because of some technical reasons, but you can still say something about the dimension of that. It should roughly be some constant dimensional thing. So that's another version. And then people have... so the epsilon here means that it's not precisely in a low dimensional space, but it's very close to 1, yes. Yeah, so the tubes have diameter epsilon. Right? The tubes have diameter epsilon, and that's what depends on. Okay, right. And then people have studied a lot more things. So for example, you can try to talk about other objects than lines. So we know there's things about ordinary circles. So an ordinary circle is one that contains exactly 3 points. Ordinary convex contains 5 points, and so on. We don't know about ordinary cubics or higher degrees. So for degrees 3 or more, we don't know if these things exist. Like if every point set that's not contained in a cubic should have an ordinary cubic. We think it should be true, but we don't have any way to prove it. Okay, good. Right, so a lot of these results, the recent ones, so that was it for the incidence bounds. I'll start talking about some of the proof methods. So a lot of these results use these things called rank bounds for design matrices. So you go from an incidence problem to a rank bound, and the basic framework is the following. So I have this matrix V where the ith row is basically my ith point. And now I want to say, well, I want to bound the dimension or the rank of this matrix in some way. So, and here's the big idea, I guess, that if 3 points are collinear, you have some coefficients such that this thing sums up to 0. And we're going to construct another matrix A, whose rows are basically going to be the coefficients coming from collinear triples. So I have my matrix of points, and then I take collinear triples, and for every most collinear triples, I'll add these coefficients and get this new matrix A. And like I said, I want to lower bound, I want an upper bound on the rank of A, and what I'm going to do is lower bound the rank of, I want to upper bound the rank of V, and what I'm going to do is lower bound the rank of A. Right. Right. So we need A to have some special property. So the triples we're going to select are going to be somewhat special in the following way, is that I'm going to make sure A is what we call a design matrix. And I'll say what it is now, but eventually what we'll do is lower bound the rank of A. Okay, so what's a design matrix? I have an M times N matrix. There's 3 parameters. I call it a QKT design. If every row has support size at most Q, every column has support as size at least K, and the support, this is the main point, that the support of any 2 columns intersects in at most T entries. So, okay, and usually T is going to be small. So what this is saying is the support should intersect in few entries, and then we should be able to say something about the rank of the matrix. So notice that we don't say anything about the values of the entries. We just care about the 0 non-zero pattern. So just based on this combinatorial information, we can get a pretty good rank bound on the rank. Well, here's an example. So, or not an example, but an illustration. I have q non-zeros in every row, k in every column, and any two columns intersecting at most t. Now, and then we can get this rank bound on the matrix. So, some rank bound, but what you want to think about here is the following. Think of q and t as constants and k as linear. And now, going back here, this term just turns out to be some constant. So what we're saying is if I have a design matrix with q and t constants and k is linear, then roughly the matrix has almost full rank. So that's pretty surprising and very strong property, and that's what we end up using to get this very sharp bounds. Yeah, so I'll talk about the proof idea here. Right, so here's an easy case when A is a 0, 1 matrix, for example. So I look at A transpose times A, get an n times n matrix, and what do I know about this matrix? Well, because every row has every column has at least k non-zeros, the diagonal entries are at least k, the off-diagonal entries are at most t, and yeah. So these are called diagonally dominant matrices, and it's fairly well known how to bound the rank of such matrices. So here's a lemma that sort of does that. It's folklore, and it's really not too well. It's not too hard to prove. So, but roughly, well, these are the diagonal entries: n squared, l squared, and mij for I not equal to j. That's the off-diagonal entry. So this is going to be small, and the diagonal entries are going to be big, so forces the rank to be large. And the proof is basically looking at the trace, and then, yeah, so that's the trace of the matrix, and then this inequality is just Cauchy-Schwarz. So looking at the trace plus Cauchy-Schwarz gives you a nice proof. Yeah, I don't want to talk too much about this, but so yeah, so for 0 non-zero 0, 1 matrices, it's really easy to get a nice bound. But remember, we don't care about 0, 1. Our entries could be arbitrary, and things get a little bit more complicated. So we'll talk about that now. Right. So for general case, we try to reduce it to the easy case. So here's what I'm going to try to do. I'm going to find R and C full rank such that this product RAC has roughly balanced coefficients. And if I can do that, then things should be nice, and I'm back to my easy case. So, right. So basically what this balanced here means, it means that the row sums are going to be, say, 1, and the column sums are going to be m over n, where you have m columns and n rows. You'll see why this comes up. But so this is going to force things to be nice, but if I can do this, I can do the same thing I was doing before. And what do I know now? Well, I know that the diagonal entries are m over n, and I can, because of the design properties, we can bound the sum of the off-diagonal entries to be small. And once again, we go back, plug it into the rank bound, and get something nice out of it. So fairly straightforward. But yeah, so yeah, the question is, can we do this, and when can we do this? So this goes back a fairly long time to some results in combinatorial optimization. Right, so yeah, and this is called matrix scaling, so it's been known for a while. This is what we rely on to find those matrices R and C. Right, so let's take an easy example. I have, say, the adjacency matrix of some bipartite graph. So here's my graph G, and here's an adjacency matrix, and I try to do basically the most naive thing. So, well, since it's n by n, I want both row and column sums to be 1, and I do the most naive thing possible. I just multiply the rows by some scalar to normalize the sums, and then see what happens. So I hope, yeah, good. Well, so I start off with this guy, and now I normalize all the row sums. Right? So this is what I get. But things don't really work out because what happens? Well, I messed up the columns. So if I try to fix the columns, okay. Well, now I messed up the rows, so let's try to fix the rows. And now I messed up the columns. And you can keep on doing this. Oh, I think I went back. Okay, good. Yeah, that makes more sense. And you can keep on doing this. But eventually, you'll notice that these entries are going towards a half, and this one's going towards a 0. So in the limit, you're going to get something like this. Well, there is no limit because it doesn't really converge, but you're going to keep flipping between these two. So that doesn't work out. Not in this case, at least. But it turns out that for a special case, things do work out, and that's a theorem of Sinkhorn. So Sinkhorn says the scaling algorithm converges if A has no zero minor, no large zero minor. So if there's no minor with size A times B, where A plus B is larger than N. And this sort of goes back to the graph having a perfect matching. Right, so I have this, so let's take a new graph, G prime, and now G prime has a perfect matching, so things should converge. And going back to the matrix, doesn't have any big zero minor. So, right. And I try to do the same thing. I do normalize the rows, normalize the columns, rows, and yeah. And now things seem to be working out nicely because all the diagonal entries hopefully going towards 1, and the rest are going towards 0. And if you do it enough times, it works out. That was matrix scaling. So it turns out that because of this perfect matching condition, so this is Hall's theorem, graph have a perfect matching if and only if there's no large zero minor in the corresponding matrix. Because of this condition, we can get that this matrix scaling algorithm always converges. So going back to the rank bound, we have to fiddle around with the matrix a bit more, where you can make sure that it satisfies this condition, and then just use the scaling algorithm and make sure things work out nicely. And no, but I think that's the end of my talk. Oh, good. Thank you. It uses a lot of topology, so uses some Euler characteristic type arguments always. Yeah, so it doesn't really make sense. Yes?
Did Green and Tao prove that if the number of lines is 1 minus epsilon times n over 2, then the picture is like the configuration except are off by delta?
Right, so that, they actually show that, yes. Yeah, so the only way you can achieve NO2 is by this,
No,
and if it's, so it's off.
If you're close to n over 2, then you're close to the...
Yeah, they also show that, yes. So their theorem is actually much, much stronger than, yes.
What happens when you iterate, when you consider the number of points of intersection of the lines determined by your set of points? What is known about the size of that set compared to your original set of points?
I could not say. Yeah. I don't know.